In this fifth lecture on AC circuits, today we shall discuss LC circuits. That is a circuit comprising of a pure inductor of inductance L and the capacitor of capacitance C, and the combination is fed by sinusoidal AC source. The combination may be series combination or a parallel combination. As for example, we first consider the series LC circuit. This series LC circuit has a very important in electronics and is generally known as tank circuit. This circuit can be used to generate a single sinusoidal outputs, pure sinusoidal output. In that sense, it is the electrical analog of a tuning fork, and this circuit can also be used in to pick up a particular frequency from a signal which is an admixture of a large number of frequencies. We shall explain these things. Let us first series LC circuit. The circuit diagram is this. Since the circuit is a series circuit, we use the reference current. As usual, we first solve the EMF equation. The EMF equation is VL plus VC is equal to V, which is equal to V0 e to the power j omega t. This is the source voltage, equal to V0 e to the power j omega t. This is known as L di dt, and this is Q by C. On differentiating this, we get L d2i dt2 plus I by C is equal to j omega V0 e to the power j omega t. This is the basically the EMF equation. The CF is obtained by setting this equal to 0, and the CF equation is d2i dt2 plus I by C is equal to 0. This is written as d2i dt2 plus omega 0 square I is equal to 0. The solution is ICF is equal to some constant A e to the power j omega 0 t plus phi 0, where omega 0 is equal to 1 upon square root LC. And for PI, we write the solution as I is equal to I0 e to the power j omega t. And if we use this Satral solution in it, we get minus omega square L plus 1 upon C I0 is equal to j omega V0. We have omitted the e to the power j omega t part. So I0 is equal to j omega V0 1 by C plus minus omega square L. This is j times V0 by where X is this. So we write the summary over here. IPI is equal to J V0 by X e to the power j omega t. This was the expression for I0. We must write e to the power j omega t to get the instantaneous current, where Ix is equal to Xc minus Xl is equal to omega c minus 1 by omega L. Now, one thing is what happens to IP at omega is equal to omega 0. These two terms cancels. These two terms can note the correction. These two terms cancels, and we have at omega is equal to omega 0. X omega 0 is equal to 0, and Pi goes to plus infinity. Sorry, plus infinity. Goes to plus infinity. For omega less than omega 0, for omega less than omega 0, this part is higher in magnitude. Xc is higher than Xl. Oh, I have written it here wrongly. Note the correction. At omega less than omega 0, X is positive. X is positive, and we have X is positive. We have X is greater than 0, and since X is greater than 0, this part is IPI particular integral omega less than omega 0 is equal to j v0 x e to the power j omega t. This is v0 by x e to the power j omega t plus pi by 2. So we see that the current leads over the voltage, and so the conclusion is I leads over V. So the circuit is, as a whole, the circuit is, since capacitive part dominates, it is capacitive. And for omega greater than omega 0, X is negative, so we write IPI for omega greater than omega 0 is equal to minus j v0 mod x to the power j omega t. This is v0 by mod x e to the power j omega t minus pi by 2. So we see that I lags behind. I lags behind V. The circuit as a whole is inductive. Let us first explain this from Phasor diagram method. We know that Phasor diagram, since this is a series circuit, the reference, we should consider reference current. So for reference current, VL is ahead of I and its magnitude is x, and for at the corresponding C, this is BC lags behind I and its magnitude, since its magnitude is minus XCI. This minus sign because it lags behind I, so the arrow is downward. So we'll draw the Phasor diagram at omega is equal to omega 0. This is the reference current phasor. This is VL phasor, and this is VC phasor, which are equal and opposite. So the resultant would be simply this one. A current will flow in the circuit without any opposition. That's why the current shoots up. And for omega less than omega 0, this is the reference current. VC will have a larger magnitude, so VL will be smaller one. This is VL, it's smaller, and VC will have a larger magnitude. So the circuit effectively becomes capacitive. So I leads over V, and the circuit is capacitive since the capacitive part dominates over the inductive one. And for omega greater than omega 0, the circuit, the phasor diagram is like this. Here VL dominates, and VL has a larger magnitude compared to VC. So the circuit effectively becomes an inductive one. This is I, this is V. So I lags behind V. And now we come to the some critical discussion on it. It is far, if we draw the particular integral of the solution, the particular integral of the solution is IPI. It shows that the current shoots up to infinity at omega is equal to omega 0. This is the omega axis, and this goes to infinity. If we want to find out a particular frequency, say we know the frequency is omega 0 is, we know that omega 0 is known. So we adjust the circuit parameter, that is the L and C, in such a way that the omega 0 is this, that is, it is given by 1 upon root over LC, and the signal, we want to pick up a particular signal, that composite signal is fed over this, and a current measuring instrument is attached with the circuit. As we change the frequency, it is found that the current shoots up to very high value at omega 0. So we can pick up that particular frequency from the composite signal. Other thing is that if we set some current in the circuit and remove the source of EMF, then the circuit oscillates an undamped motion, this. This is an undamped sinusoidal motion, which can be considered as the oscillator which gives rise to monochromatic signal of frequency omega 0. Now the thing is that one thing we haven't considered till now, that in reality the L and C's have some series resistance associated with it. So the total resistance of the circuit, I will need this expression and this expression. So for a real inductor, it can be considered to be a inductor L plus a small resistance RL. So this is a real inductor, and the real capacitor is 1. Apart from this, some extra resistance may appear due to the resistance of the wire or from the junction, which is we call RW. So the total resistance of the circuit will be RL plus RC plus RW. For good quality of inductor and capacitor, these two are really small. This can be minimized to a great extent. However, R is a non-zero quantity, so some energy will be dissipated across the resistor. Since L and C, pure L and C are not lossy elements, the current shows a undamped sinusoidal motion. When this if we consider the real inductor and capacitor, it will have a resistance, and we define a quantity twice B is equal to R by L, and in that case this CF will be augmented. This CF will be augmented by a factor BT for real L and C. It will be augmented. Another thing will happen in that case, this X, the X factor, this X factor will change. So the X factor will become like Z is equal to R plus JX minus JX. So the magnitude of Z will be R square plus X square square root. At resonance X is 0, and the current, peak value of the current, this will be restricted to V0 by R. It's a finite quantity. Since small r is small, it is high but a small quantity. So if we consider a practical circuit comprising of capacitor and inductor in series, the oscillation in the circuit, the oscillation coming from the CF part will die down with time, but as the damping is small, it will take considerable time to die it out, and the resultant motion will be one given by this IP part. Obviously with this augmentation shown in red color. Otherwise, had it been an undamped motion, that is no resistance, then the total solution would be the combination of CF and PI, and both of them, if both of them are sinusoidal, so the resultant will be the superposition of two sinusoidal oscillations, which will form a beat, and the current will no more in the circuit will no more be sinusoidal, but it will be a periodic one, and the time period will depend inversely on the difference of the frequency. The time period is omega 0. A 2 pi factor will be there. Now come to the voltage gain. If we calculate the voltage gain, we see that we define with a minus sign. The cause of minus sign is that we have defined x as equal to xc minus xl, but the actual voltage is V is equal to J omega Li minus J I by omega C. J is there, so this is J because we have defined x in this fashion, so this is the minus sign is due to this reason. If we if we multiply both the numerator and denominator by omega square and divide by L, so we get omega square minus omega 0 square. Since we multiply both numerator and denominator by omega, it's become omega square, this is base free from omega. We divide by L, so L goes and it is 1 by LC, which is this. So we see that voltage gain becomes infinite at omega is equal to omega 0. Note that in calculating voltage gain we have considered only the PI part, because in real circuit the current corresponding to the CF part, that is dies out with time, and the circuit ultimately oscillates with the frequency of the external source. Similarly, we can define this and proceeding the same procedure we follow. Both the gain curves have this nature. It's not symmetric, only asymmetry is there, and this is omega 0. So we see that the voltage gain rises very rapidly to a very high value at omega is equal to omega 0, and this can be used to pick up a particular frequency out of a combination of frequencies. That much with the series LC circuit. Now we shall take up the parallel LC circuit. A parallel LC circuit with parallel combination. That is, we consider parallel LC circuit. The circuit, let me first draw the circuit diagram for it, and then I shall analyze it in the same fashion. Since it's a parallel circuit, we use the reference voltage mechanism, and the current flowing through it is IC, and that through L is IL. These are the phases. The current equation is we are adopting the differential equation formalism. For IL, we know that VL is equal to L DIL dt. So IL can be written as 1 by L VL dt. So this is 1 by L VDT. We have omitted the L suffix with V because same voltage is applied to both the circuit elements, and for this VC is equal to Q by C, which gives you Q is equal to CVC, or IC is equal to C dVC dt. So this is again no subscript. Now we differentiate it with respect to time to get this part gives you C d2v dt2. This part gives you V by L is equal to J omega I0. The CF is C d2v dt2 plus V by L is equal to 0, which leads to V is equal V as a function of t, a e to the power j omega 0 t plus theta 0. This a is different from that e which we used in the case of series circuit, and omega 0, but the omega 0 is the same. So this is the natural frequency, and for Pi we write V is equal to V0 e to the power j omega t, and we substitute this in this equation. So we get minus omega square c plus 1 by L V0 is equal to j omega I0, or V0 is equal to where B is the susceptance is defined as in this connection. Let me write few things. We have used Z is equal to R plus Jx. This is resistance, this is impedance, this is reactance. We have also defined Y as 1 by R minus J 1 by X. This is admittance. admittance, and 1 by x is B. This is susceptance. These are the four quantities that we have used in addition to the resistance. So now come to the point. V0 is this. So we get VCF as Pi as a function of t is equal to this part where B, the susceptance B is defined as omega c. Now at omega is equal to omega 0, B is 0. At omega is equal to omega 0, B is equal to 0, and Vpi shoots to infinity. Again, for real L and C, it will have a it will come down to R by I0. At omega less than omega 0, at omega less than omega 0, this part is larger and this part is smaller, so B is negative. B is negative at omega less than omega 0. B is negative. And we can write Vpi as minus j I0 mod B e to the power j omega t, that is equal to I0 mod B pi by 2. And sorry, it is not at 4. B is positive, and let us now draw the corresponding phasor diagrams. Please note few corrections. If omega is less than omega 0, this denominator is small, so this is a wrong conclusion was drawn, and this is plus, and so this is plus. And for this part, please note these two corrections. Now we come to the corresponding phasor diagrams. At omega is equal to omega 0, the phasor diagram for parallel LC circuit. We know that first thing, let us recapitulate that if VB, this is the reference voltage phasor, then IC is ahead of V and IL lags V, and the expression is given by this is XC magnitude these are the expression for the currents now you see the using this we draw the Phasor diagram at omega is equal to omega 0. This is the reference voltage. This is IC and IL has the same magnitude. IL has the same magnitude, so the circuit effectively becomes this voltage, which explains this phenomenon. For omega less than omega 0, IL is greater than IC. This is reference voltage. IL has a larger magnitude, so the effective circuit is this is V, this is I. So we see the V leads over I. So here we forgot to write V leads over I. The circuit is inductive. And here we see that V lags behind, V lags behind I. The circuit is capacitive. The circuit is as a whole capacitive. So we have proved that this is the part and the circuit is indeed inductive. P is ahead in phase over I. Now come to the third situation. For omega greater than omega 0, this is voltage phasor at a particular instant. At the same instant, IC is here. IC has a larger magnitude, which is obvious from the expression for IC and IR. IC and IR. IL, so the circuit effectively becomes I is ahead of phase over V, so V lags behind I. The circuit is capacitive. So we have solved this problem also, and we can similarly define current gains which will have the similar behavior as the as of the voltage gain, which shows a shooting off at the resonance frequency and then falls on either side and can be used as a band pass filter. That's all with LC circuit, and in the next class we shall take up L series LCS circuit.